Welcome to our ninth session on measure theory. This is actually ninth. I mistakenly numbered them wrongly. Okay, I forgot the candle set was one of the thing. It was the sixth. So we are given 7 and 8. Two sessions on Lebesgue measurable sets. This is going to be the third session on Lebesgue measurable set. And in our ninth lecture on Lebesgue measure theory. Okay. So let us get started. See, I had been forgetting in the very first session on Lebesgue measurable set, I wanted to prove something which I forgot. And I thought I will do it in the second, then again I forgot. So I think I should start with that so that I don't forget it. It is about the measurability is translation invariant. That is, if E is measurable, if you translate the set E by a vector, by a real number A, then A plus E is still measurable. Of course, the measures will be the same. Do you remember in our intuitive idea, this is one of the important criteria, right? For extending length to measure, what should satisfy? Translation invariant is first. First condition is measure of the interval must be length of the interval, and the measure should be translation invariant. Okay. Third thing is it should be countable additive. Okay, these are the things. Anyway, let's get started. So I talked about the correction. Okay. So what we want to prove is let E be a subset of R or Rn. Okay. Then we want to say E is measurable if and only if A plus E is measurable. Remember, we introduced the translation A from Rn to R to R by TA of X is A plus X or X plus E. Okay. Therefore, my A plus E is nothing other than TA of B. Alright? Okay. Recall that. Now, when I want to say, suppose E is measurable, we will prove one way, the other way around is exactly similar. I want to know whether A plus E is measurable. Did I start my recording? Yes. So I want to say whether A plus E is measurable. Okay. So to check whether A plus E is measurable, Cartesian definition demands if you see F is any subset of R, then M star of F should be equal to M star of F intersection A plus E plus M star of F intersection A plus E complement. This is same as M star of F remove A plus E. This is what you have to check. Okay. So what are the basic ideas we can think of? The first thing we know is, from our earlier knowledge, we know if E is any subset of R, then outer measure of E is same as outer measure of A plus E. This we know. Okay, known. So somehow we should relate these measures instead of A plus E. We know the measurability. What we know is this one we know. M star of F is M star of any set, let us call it G. G is any test set. Okay, M star of G intersection E plus M star of G intersection E complement or G minus E. Right? This is for any test set. So the idea is somehow we should bring it to that fashion. Okay? And so let us look at F intersection A plus E. Right? Yeah. So what we want to say is that, okay, T minus A of A plus E is simply minus A plus F intersection E. Okay. Please check, this is trivial checking, right? Because you start with any x here, x is in F, therefore it will be minus A plus x. Therefore that is in minus A plus F. And next is, if x is in A plus E, okay, x is A plus E, therefore it's A plus Y, therefore this will be x minus a will be y, which is in E. You understand that? Therefore, okay, this is the thing. And similarly, other way around, minus ta of f intersection a plus e complement, which is same as t of minus a f minus a plus e, is nothing other than f minus a plus f intersection t. Okay, please check these things. I checked one, similar thing we have checked it, right? Therefore, let's look at what is m star of f intersection a plus e. Therefore, this is, notice that this object, okay, is translation by minus a of this object. Therefore, outer measure of this fellow is same as outer measure of t of minus a of this object, f intersection a plus e. Okay, but that we know is nothing other than m star of minus a plus f intersection e. Similarly, m star of f minus a plus e is nothing other than minus of minus a plus f minus e. Right? Now let us take my test set to be minus a plus f. Measurability of E will say m star of minus a plus f equals m star of minus a plus f intersection E plus m star of minus a plus f minus e. Yeah? Is that clear? This is because of measurability. Hold this. But this object we know is nothing other than m star of f intersection a plus e, and this we know is m star of f intersection f minus a plus e. Okay, but by translation invariant left hand side, this fellow, that is m star of minus a plus f, is same as m star of f. So we have proved m star of f equal to this. For any test set f, a plus e cuts it into two pieces and their outer measures add up, right? So this shows that a plus e is measurable. Okay, and since outer measure is invariant, m star of e, this is measurable, therefore this is nothing other than m of a plus e, but this is same as m star of e, but since e is measurable, this is m of e. So what we have shown therefore is, we have conclude if e is measurable implies a plus e is measurable for every real number a, and measure of a plus e is measure of e. Converse is exactly the same. Yeah, you start with this, call it as, if you want, call it something like okay, a, capital A, then apply this. Okay, a, if you take minus a, you will get e. So it is an if and only if. Do you follow that? The same argument you apply to the set a plus e with the translation minus a. Okay, therefore if a plus e is measurable, translation of a plus e by minus a, that will be e, that will be measurable. Okay, that follows. Okay, so we have proved this is if and only if. So pause, review, proceed. So please go through the argument. It's very simple, but I find that many machine theory books do not even give this thing. Okay, people assume, but it's very easy. Okay, you can see how we argued that. Okay, we wanted to say outer measures invariant translation. Okay, that's one thing, and E is measurability. So we just manipulated Okay, arrange the matter symbols in such a way that things drop out. Okay, if you try to go through line by line, you try to remember. Don't do that. Okay, try to understand what we want to do, what are the facts we know, and I want to use it to prove the result. Then it becomes easy. Okay, okay, we will continue to the next one. So the next thing we want to prove is something which we saw in the first few lectures on intuitive ideas. Do you remember one of the conditions? Try to understand, these are not important for exam purpose, but it is important for a thorough understanding, in-depth understanding. We said if I extend length to measure, okay, on a large class of subsets of R, one of the things I wanted was if En increases to E, okay, then I want a measure of En should increase to measure of E. And we also said if A1 to An are pairwise disjoint and measure of the union AK k equal to 1 to N should be equal to some measure of AK k equal to 1 to N. These are the desired properties. Desired properties are criteria of a measure. Okay. In fact, then at the time I said these two conditions can actually be replaced by what we call countable additivity. Because this is important, because most of the area of the geometry figures from ancient times was computed by means of exhaustion. If I have something like this, you keep on exhausting by known pictures. Okay, and then the area should reach, you should get the area. That is the reason. And this is a very standard one. If I have two kind of disjoint thing, the area should add up, right? That's again intuitive property. Because of those two properties only we needed. But what we actually proved was a measure on the class of measurable sets. This is countably additive. This we proved. Now what we want to prove is the following. Suppose my An increases to A, and An's of course are all measurable. Okay. Then I want to say A is measurable and limit of measure of An is measure of A. Okay. So what does it mean to say An increases to A? Let us make sure that this simply means An is contained in An plus 1 for all n, and union An is A. That okay. So An increases to A. This is the definition. Okay, right. So the trick is, what we do, think of this. This is my A1, A2, this is my An, and this is my An plus 1. Right? So we want to use countable additivity. Right? So what we do is we define B1 to be A1, okay, this one, B2 to be A2, okay, this is my B2, okay, B2 to be A2 minus A1, and what will be my Bn plus 1? That is going to be An plus 1 minus An. That is this object. Right? Now notice that each of these things are measurable. Also, Bn as n where is is pairwise disjoint, and union Bn is union An, which is A. Okay, these are the claim we want to prove. This is actually set theory. It's very easy. So take a minute, pause the video and try to do on your own. If you don't get, come back. Did you get it? Let's go. Okay. Now, this Bn is measurable is very clear. Then this is the pairwise disjoint, because take any m and n, assume with our loss of generality m is strictly less than n, we want to show this intersection is empty. Right? But notice that Bm is am minus 1, and this is an minus an minus 1. Since m is less than 1, notice that n is greater than or equal to m minus 1. And therefore, am minus 1 is contained in an. Right? And am also contained in an. Do you see that? Therefore, this is okay. I want to say this is empty. Right? Suppose x belongs to this. This means x is in am to start with. Right? But then, if this says, if x is here, it says x is not in an minus 1. But that contains am. Yeah, that's a contradiction. Therefore, this is empty. Do you understand this? Pause, review, proceed. Okay. Therefore, we have proved this pairwise disjoint. Second thing I want to show is union Bn is union An. Okay. Notice that this is clear because each Bn is a subset of An. Therefore, their union will be contained in this. This is clear. So, I have to prove this way. So, let x belong to An, right? Union An, sorry. Let x belong to the right side. Let x belong to here. I want to say x belong to Bn. Right? Look at the picture. Now, we know Ans are increasing. So far, we have not used the fact. We have used the fact earlier here. Yeah. Ans are increasing, right? Therefore, x belong to union An. Okay. Therefore, I can look for, that means there is at least one n such that x is in An. Right? Therefore, let capital N be the least positive integer such that x belong to An. That means x is not in ak if 1 is less than or equal to k less than or equal to n minus 1. Do you understand this? Why this is possible? The set of n such that x belong to An is not empty. This is a subset of natural numbers. Therefore, by well ordering principle, there is n is the least element. Okay? Right? Therefore, this x is not in any of the previous AKs. Is that clear to you? Very good. Now, therefore, let us look at this. So, what am I supposed to do? So, my x belong to union An. Therefore, x belong to capital An, and x is not in AK 1 less than or equal to k less than or equal to n minus 1. Okay. Now, I want to say x belong to, therefore, Bn. Yeah. What is Bn? Bn is An minus 1. Right? X belong to An. X is not in An minus 1. Therefore, x belong to Bn. That means x belong to union Bn. Therefore, we have proved union Bn is same as union An. Okay? So, we have done that. Now, let us look at this collection Bn. Therefore, this collection, as I saw, is pairwise disjoint measurable sets. Right? Therefore, and union Bn is A. Right? Therefore, by countable additivity, measure of A is equal to measure of Bn, n from 1 to infinity. This is by countable additivity. T of m. Right? Okay. But what is measure of Bn? Measure of Bn is measure of an minus 1. Okay. Now I want to claim this is nothing other than measure of an minus measure of an minus 1. We want to claim this. Okay. An minus 1. This is very easy. More generally, if A is a subset of B, nothing to do with the A above A and B. Okay. This is general. Okay. A and B, and assume they are measurable sets. Okay. Then measure of B is measure of A plus measure of B minus A. This we want to claim. Why? Because A and B are measurable, therefore B minus A is measurable. And A union B minus A, okay, this is a disjoint union, and their union is all of B. Therefore, by countable additivity, by finite additivity, measure of B equal to measure of A plus measure of B minus A. In particular, measure of B minus A is measure of B minus measure of A. Yeah? Right. Right. But notice that if I want to do certain things, okay, I would like to say these are not infinite, because if measure of B is also infinite, measure of A is also infinite, then I have to make sense out of that. Okay? Do you understand that? So this is true if, since A is contained in B, if I assume that measure of A is finite, then I can do that. Measure of B could be infinite, I don't care. Yes? Okay. So let's go back. So what I have done, therefore measure of Bn is measure of an plus 1 minus measure of an is measure of an plus 1 minus measure of an. Now let's look at, so there is still a problem. As you could see, this is valid only if measure of an is finite. Okay. Now let's look at, if measure of an is not finite, okay, then measure of an plus 1, we will come to that. Okay, let's assume this for the time being. For all n, assume this for the time being. Okay, now let's come back. Therefore, measure of Bn, measure of A equal to summation measure of Bn to infinity, that is going to be measure of A. Let us assume that my A0 is empty set, therefore B1 will be empty set. B1 will be A1 minus An minus 1, which is A0, which is A1. Okay, this is going to be measure of An minus measure of An minus 1. Okay, but this is going to be, let us look at that, measure of A1 minus measure of A0 plus measure of A2 minus the measure of A1, and so on. The last one will be measure of An minus measure of An minus 1. This is the nth partial sum. Right? So you can see they all get cancelled. Okay, therefore this is equal to measure of An. So nth partial sum of summation measure of Bn. This is a telescopic series is what we are saying. Okay, is measure of An. Right? Now what is the definition of the sum measure of Bn? This is the limit of nth partial sums. But that is equal to measure of limit of An. but this is measure of A. So we have proved, okay, limit of an equal to, limit of measure of an equal to measure of A. And notice that since an is contained in an plus 1, etc., this series is actually increasing. Measure of an increases to measure of A. So proved. And this we proved only under the assumption at least each of an is a finite measure. What does it mean? For all n, m of an is finite. Okay, suppose one is infinite. Suppose measure of an is infinity for some n. Then since an is contained in n plus 1, right, and which is contained in A, therefore measure of A will actually be, okay, limit of measure of, let us call it A capital N, okay, measure of limit of an, which is equal to limit of measure of an plus 1, an, measure of an plus 1, etc., but each one of them is infinite. So in either case we have shown that, okay, if an increases to a's are all measurable, then A is measurable, and measure of an increases to measure of A. By the way, how did we prove that this is measurable? Okay, that's because we said my A is union of Bn. Yeah, we proved A is union of Bn. This is my A, this is union Bn, these are all measurable. Therefore, countable union of measurable sets is measurable. Therefore, A is measurable. So also we proved on the way. Okay, please go through this argument. Pause, review, proceed. Hi, this is continuation of measure theory 9, measurable sets 3. Actually, I am continuing the next day due to some work. I have to stop in between and I have to leave. And today I already did, and somehow it seems to be jinxed. Okay, first time I didn't wear this. Second time I forgot to turn on the recording. Third time, while I was recording, the battery went dead. So whatever I lectured for about 40 minutes I already lost. At least 30 minutes. So let us see, this time I don't get any jinx. Okay, and this happens many times. Okay, it's not easy going. Anyway, let's get started. Yeah, so in the we saw if an's are measurable, and if an increases to A, then A is measurable, and we proved measure of an increases to measure of A. This is what we proved. Okay, call it a part 1. Okay, this proof actually, the way we showed A is measurable is interesting. Okay, see, the way we showed was, remember, A was union An, and what we did was we showed it as union Bn, where Bn's are disjoint, pairwise disjoint measurable sets. Because what you have shown us, if En's are pairwise disjoint, and then E equal to union En is measurable, and measure of E is summation measure of En. This is what you have shown. So we made use of that. So the only way we proved union An is measurable is to express this union as a countable union of pairwise disjoint measurable sets. Okay, so this can But here we made use of the fact ANs are increasing, but the proof actually shows something more. So let me just put it as a lemma. Okay, let AN be a sequence of measurable sets, countable family. Then we claim there exists another countable family N, okay, countable family of pairwise disjoint measurable sets, such that union AN is union BN, and union BN is measurable by the theorem. This is the theorem. Oh, yeah, good. I'm doing screen sharing. I'm not very sure now today. Yeah, this is all right. And hence, we can conclude union AN is measurable. And hence it has a corollary. We see that intersection AN is also measurable. Why? Because union AN complement is measurable. Because AN is measurable, therefore AN complement is measurable, and by this theorem union AN complement is measurable, therefore its complement, namely intersection AN, is measurable. So that follows corollary. So I only have to prove this. Yeah. Now that's very easy. What we did last time, the same thing we are going to do. Let B1 be equal to A1 and B2 equal to A2 minus A1 and B3 equal to A3 minus A1 union A2 and so on. So whatever is earlier, you remove that. So what will be general Bn? Bn will be An minus union 1 to n minus 1 of AK. That's it. Okay. Right. Now we claim Bn. First notice that these are all measurable. If Ans are measurable, this is measurable. Therefore, this intersection, okay, this complement is measurable, and AN intersection, this complement is measurable. Okay, therefore Bns are measurable. So, next we want to say that Bns are pairwise disjoint. Okay, so let us assume n is not equal to m. As usual, assume the loss of generality, m is less than n. Right? Then let us look at Bm. Now Bm is already contained in Am because this is Bm is Am minus A1 to Am minus 1. Right? Therefore it's contained in Am. But Bn is An and I am removing A1 to Am. An minus 1. Therefore my Am will be somewhere here. Right? Yes? Right. So these are pairwise disjoint. Next thing we want to show is union AN is union Bn over n. In fact, we will prove something much stronger. Union AK, k equal to 1 to n, is union BK, k equal to 1 to n. Look at the thing, or the way we define, whatever we missed is already caught. Okay. Notice that each BK is contained in AK. Therefore, union BK, k equal to 1 to n is contained in union AK, k equal to 1 to n. So I only have to prove this inclusion. So let X belong to union AK. So let L be the least. Okay, that means X belong to some AI, right, for some I between 1 and n. Least I, so that X belong to AI. We know that X belong to union, therefore set of I so that X belong to AI is non-empty, and that's a subset of natural number. Therefore L is L is the least. This means what? X belong to AL, but X does not belong to AK 1 less than equal to k less than equal to L minus 1. That means X belong to L minus A1 union AL minus 1, but that is BL. But right? Yeah. And what is this L? This L is between 1 and n. Yeah, this L, this. Okay, here. Therefore, x belong to L for some there exists L such that 1 less than equal to L less than equal to n. That means, yeah. So if x belong to union a k equal to 1 to n implies x belong to union b k equal to 1 to n. It actually belong to BL. Okay. So what you have shown therefore is you have proved the result. So pause, review, proceed. Okay. Now let's come back to the counterpart of 1. That is, the first one said if ANs are measurable and AN increases to A, which is union AN, then we know A is measurable because of this lemma, or even otherwise, then measure of AN increases to measure of A. This we proved. Now what is the counterpart? Counterpart is if BNs are decreasing to B is intersection BN now, right? Then I want to know whether measure of Bn decreases to measure of B. Okay, this is what we want to prove. Right? So, like in mathematics, what we do is we try to reduce this problem to earlier seen problem. Since Bn, we had already proved An increases to A, we have proved the result. Therefore, I want to prove the result for Bn decreases to B, so I convert it. The picture is very clear. So suppose I have my B1 here, right? Therefore my B2, this is my Bn, okay, and this is my Bn plus 1. Right? Therefore if I define my AN to be B1 minus Bn, you can see AN is increasing and each AN is measurable. Is that clear? So let us look at, if x belong to AN implies x belong to B1 and x is not in Bn. But remember, Bn plus 1 is contained in Bn, therefore this implies x belongs to B1 and x not in Bn plus 1. That means x is in An plus 1. So we had actually proved it. Pictorially it is very clear because you can see An is going to be this. Okay, B1 minus Bn. This is my. But whereas An plus 1 is going to be this. Right? Pictorially it's very clear, we have a proof now. Right, very good. So, by part 1, and this looks like point. Part 1, so An increases to A and measure of An increases to measure of A. Right? But what we wanted to prove is measure of Bn decreases to measure of B. So we have to understand what is the relation between these 4 objects. Actually infinitely many, for each n I have to know, but I am just saying that. Okay. Now look at An. What is An? An is B1 minus Bn. Each of them are measurable. Okay. Therefore we know, we had already seen this is nothing other than measure of An equal to measure of B1 minus measure of Bn. Right? Okay. But notice that this will make sense only if, okay, one of them is finite, right? Either this is finite or this is finite. And so remember, Bn is already contained in B1, therefore we can as well assume measure of B1 is finite. One of them has to be finite, right? I can assume this has to be finite. If that be the case, I have to start differently. So let me start with m of B1 itself is finite. Okay, so measure of Bn I had understood. Now let us look at measure of A. What is A? A is union An. And what is An? That is union B1 minus Bn. Right? I claim this is nothing other than B1 minus B. Again, try to have some kind of intuition. We will prove it rigorously. Right? See, this is my B1 minus Bn, so I keep on shrinking. So what I would expect will be whatever is I am throwing out will be common to all my Bn's. You understand that? From B1, okay, remember this is my blue ones are A1, these copy ones are An plus 1. So they are increasing. So where will they go to? What? To get An, what I have to do? I have to remove everything which is in Bn, right? And these are decreasing. Therefore, it's very clear from pictorially this must be equal to this. Okay, we shall prove this. Okay, we shall prove this. Now let x belong to A. That means there exists n such that x belong to An. So that means there is n such that x belong to B1 minus Bn. That means there is n such that x belong to B1 but not in Bn. But this implies x belong to B1 and x does not belong to intersection Bn, which is B. Okay, that is x belong to B1 minus B. Is that clear? Yeah. So we proved A is contained in B1 minus B. Now let's start with x in B1 minus B. If x is in B1 minus B, x is in B1 but not in B. Okay, but what is B? B is intersection of Bn. Therefore I am writing. Okay, that means there is at least one n such that x is not in Bn. That's what we mean. So you can see this. I can reverse the argument. That means x belong to, there is n such that x belong to B1 not in Bn. That means x is in Bn. That means x is in A. Okay, so we had rigorously proved it. What have we proved? We have proved A is B1 minus B. So pause, review, proceed. Do not assume such things. Okay, perhaps you have never done such things. Most of you, please do that. Even the best will assume that. Don't assume. Okay, so let us collect. We know measure of An increases to measure of A, and we also know now An is B1 minus Bn. Therefore, measure of An is measure of B1 minus measure of Bn under the assumption, okay, provided measure of B1 is finite. Okay, now measure of A, now we know A is B1 minus B. Again, therefore, measure of A is measure of B1 minus measure of B. Therefore, this is equal to measure of B1 minus measure of B. Therefore, what we know is this increases to this. Now, measure of B1 is finite and a constant. Therefore, I can add measure of B1 to both sides. This object. Okay, but that is minus measure of Bn increases to minus measure of B, or which is same as saying measure of Bn decreases to measure of B. Okay, pause, review, proceed. As you can see, there is a lot of theoretic things. Okay, and if you try to look at such things, either you have to memorize. The best thing is don't learn this properly. Have also pictures in mind, as I do. See, we are dealing only with R, but again and again I am emphasizing, I am drawing pictures in R too. Okay, Venn diagram, etc. So try to learn such things, and but then try to give a rigorous proof so that you will be very confident. Okay, let's go back. So what we have proved is only if Bn is a decreasing to B, where B is intersection Bn, and if measure of B1 is finite, then we have proved M of Bn is decreases to M of B. Okay. Now you may wonder, whereas in the case of increasing, we never needed such a condition. Okay, if An increases to A, we saw measure of An always increases to measure of A. We didn't have to put any condition on finiteness of any measure. Okay, here we have to put. Okay, but we have to impose such a further condition. But you could ask, maybe a smart proof exists which I will avoid. That's not the case. Why? Let us look at my Bn to be n to infinity. Okay, this is set of all x in R such that x is greater than or equal to n. Right? These are all measurable subsets of R, and Bn decreases. But where does it go to? Bn decreases to empty set. Why? Because what is intersection B? B is intersection B, and if x belong to this, when does x belong to this? X must be greater than or equal to n. That means x is set of real numbers so that for all n, x must be greater than or equal to n. That violates Archimedean property. Because x is an upper bound for n. That is, n is bounded above. That content is Archimedean property. Therefore, my B is empty. But what is measure of Bn? That is infinite. Right? Whereas measure of B is empty set, which is 0. Therefore, okay, the theorem, okay, I have to assume at least one of the Bn's must have finite measure. Okay, we assume measure of B1 is finite, but we can also assume measure of some Bn, okay, is finite. In that case, I will look at only An to be Bn minus Bn for n greater than or equal to n, and argue as earlier. This is for those who want some kind of, to understand the proof, take this as an exercise. Okay. So the result we proved is the following. If Bn's are measurable and Bn's decreases, and assume there exists n such that measure of Bn is finite, then measure of Bn decreases to measure of intersection Bn, which is B. Okay, this is the result, final result. This is part 2. And notice that intersection Bn is measurable because of the last lemma. We know that B equal to intersection Bn is measurable. Therefore, this is legitimate. This is valid. Otherwise, I cannot write measure. Okay, I may be able to write only outer measure. Okay, so pause, review, proceed. So, what are the things we have proved? The class of measurable sets we have proved. It contains intervals, right? And it contains any kind of, if I have a pairwise disjoint measurable set, their union is also measurable. Using that, we proved if I have any countable family of measurable sets, their union is measurable, and hence their intersection is measurable. right? What is their take on this? Can you think of some use? Remember we said any interval is measurable, therefore any open interval is measurable, right? Therefore countable union of measurable open intervals must be measurable, correct? Do you think of something? Is your topology good? Remember, any open set in R is countable union of pairwise disjoint open intervals, right? Therefore any open subset of R is measurable. Yeah, let us record it. Let G in R be open. I usually write U. Okay. Then we know U is union Jn to infinity. Simply n. Okay. It may be even finite. So let me write Jn where n, where Jn's are open intervals and pairwise disjoint. Therefore, any open set is measurable. As an immediate corollary, any closed subset is also measurable because by definition closed set is complementary of open set. Therefore, any closed subset is measurable. In particular, any compact set is measurable because by any oral theorem, a compact set has to be closed and bounded. In particular, it's closed. Therefore, any compact set is measurable. You see that there are a lot of interesting things, right? In particular, countable union of open sets, no problem. Intersection, suppose unions are open, okay, this is also measurable. And if Fn's are closed, then countable union of Fn, these are also measurable. It may not be closed, but it is measurable. This may not be open, but this is measurable. Okay, so let us look at a general thing. Okay, a G delta set. A set A in R is a G delta set if if A is intersection of UN where UNs are open. It is intersection of countable family of open sets. And similarly, a subset B of R is F sigma set if B is union of Fn where each Fn is closed. So what you have shown is any G delta set, any X sigma set is open. Okay, pause. See, these are very complicated thing. You cannot imagine. All right. Okay. Okay. So we have shown that this is zero. So the class of measurable sets, what are the things it has? It has any kind of interval. It has open sets. It has closed sets, and hence compact. And it has G delta. What is G delta? Intersection of countable family of open sets. Okay, that may not be open, but it's. And F sigma, this is union of countable family of closed sets. That union may not be may not be closed, but it is still. These are all measurable sets. So you can see we have a very, very, very large class of sets. Okay, the very interesting thing. Okay, so this leads to what is known as regularity of Lebesgue measure. So let us look at it. Perhaps I will take this in the next session, but let us try to understand what it says. See, when I started with the numbers in school, etc., we start with integers, negative integers and fractions. Okay, we are all very happy. But when we want to do the analysis, we found there is something missing. So we have to impose the LUB property, least upper bound property, and get what is called a real number system. We perhaps never constructed, okay, but okay, there is this a field in which I can do all field operations, and there is an order, and that order is total order, and in such a way that it has the least upper bound property. Q has everything except LUB property, right? But notice that R we may not even construct, we may not know, but with this we are able to work with that R. And the most important thing there is the set of rational numbers Q, namely okay, that is dense in R. So for any kind of real number can be approximated to whatever level of accuracy you want by a rational number. So for any scientific computations, we usually reduce to something to do with the rational number. Okay, it's much easier. Okay, but to do analysis, we needed the real number system. So similarly, to do integration theory, I need Lebesgue measure. But what we are going to prove is Lebesgue measurable set we define in a very complicated way. We want to define what is meant by outer measure. That is defined for all sets, but then we have to restrict only to class of subsets called Lebesgue measurable sets. Okay. Now what we found out was Lebesgue measurable sets contain a very large class of topologically significant subsets like open set, closed sets, compact set, G delta set, F sigma sets. Right? Now what the regularity of Lebesgue measure says, okay, it in fact characterizes my set E a subset of R is going to be measurable if only if it can be approximated by means of open sets or by means of closed sets, or it is almost equal to G delta set, almost equal to, I would interpret, I would say that later, and almost equal to an F sigma set, okay, which are easier in some sense. Okay, this is the crux of the matter. Okay, in the next session we will prove these things, but my request is don't be disheartened. There is a lot of theoretic thing. Please go through. That's why I took pains to explain each and everything. Please go through it. Okay, we will meet again in the last session. We will prove regularity of Lebesgue measure. Okay, right, stay tuned, stay safe, we'll come back.